math and beats. In this video, we're going to come up with the derivatives of the other inverse trigonometric functions, those being specifically the derivatives of the arc secant function, the arc cosecant function, and the arc cotangent function. Let's go. Let's start by considering the secant function. Why is secant of x here? So just as a reminder, here is the graph of the secant function. Of course, this is a periodic function and it continues this behavior towards negative infinity and towards infinity. Now clearly, as with most of these trigonometric functions, they are not one-to-one. So we have to define them in a particular interval to make them one-to-one and then talk about their inverse. So that's what we're going to briefly talk about here. Notice that if we look at the specific interval of x values 0 to pi, but excluding pi over 2, then the secant function is one-to-one. So you just go back up here, you think 0 to pi, which part of the graph is that? That is, okay, well here's pi right there, right? So just draw a line like so. So this region right there, right? Notice that the function is one-to-one there, except of course the function is not defined at pi over 2. So let's define our secant function over this particular interval of x values to make it one-to-one, like so. And when we do so, we could then talk about its inverse, but here's just that part of the graph that we are looking at above. Here's the secant function defined on the interval of x values from 0 to pi, excluding the x value of pi over 2. We can clearly see it's one-to-one on that particular interval. And so, what can we do? Like I was saying, since it's one-to-one on that interval, again excluding x is pi over 2, then we can define the inverse secant function like so. Say f of x is secant x, then f inverse of x is secant inverse of x, such that the domain of the secant inverse would be the range of that secant function over that particular interval, which is negative infinity to negative 1, and also union that with 1 to infinity. Notice negative 1 and 1 obtain values. And then the range is going to be from 0 to pi, where the outputs are not going to be pi over 2, right? So in other words, we're reversing the domain and range of the secant function where we defined it on the interval 0 to pi to come up with the corresponding domain and range of the secant inverse function here. When we do that, and a lot of this is just a reminder, a refresher, we get this picture. So the blue graph there is the graph of the secant function over the interval from 0 to pi. And then the green graph is the corresponding inverse, secant inverse of x. As we can see, its domain, negative 1 all the way down to negative infinity there, right? And then 1 to infinity in that direction. And then we notice that it never actually obtains the output value of pi over 2, and its range 0 to pi over 2, and then pi over 2 to pi, not including the pi over 2. So we get that picture, and we have the graph here of our secant inverse function, and we can see that where it's defined, excluding the endpoints, we should be able to find its derivative because it's smooth here. So that's what we're going to do. We are going to look for the derivative of the arc secant function right now. So what do we do? Well, very similar to how we derive the derivative of the arctangent function. Because secant and secant inverse are inverse functions of each other, then when I compose them, say secant of the secant inverse of x, we get back x, and this is for values of x in magnitude bigger than or equal to 1 as described earlier. And thus, from that equation, we can differentiate both sides with respect to x, like so right down here. And when I do that, then applying chain rule, then the left side, we're going to get derivative of the inner function, which is the derivative with respect to x of the secant inverse of x. We don't know what that is, so that's just what it is. and then times the derivative of the outer function. Now, the outer function here is the secant function, and the derivative of the secant function is the secant times the tangent function, but now evaluated at the inner function. So hence we get all this right here, the secant of the secant inverse of x times the tangent of the secant inverse of x. And that's all going to be equal to 1, of course, because the derivative of x with respect to x is 1. From here, we can isolate our derivative of a secant inverse function on the left side by dividing both sides by that secant of secant inverse of x and tangent of secant inverse of x. To obtain this right here, just take note, when I divide by secant of secant inverse of x, that is the same as multiplying by the cosine of the secant inverse of x. So we have this result now. The derivative of the secant inverse function is this ratio right over here, and we would like to clean that up so that we don't have, trig functions evaluated at inverse trig functions. And to do so, we're going to go look at a triangle again. So, of course, secant inverse of x is this function such that we get this angle theta so that the secant of the theta, that angle, is x, which of course is the same as x divided by 1. So we can look at a diagram that illustrates this, and that is this right triangle right here, such that we have x as the hypotenuse and 1 is the adjacent side of this angle, where we do not know the opposite side of this angle. So remember just a moment ago what we were saying, secant of theta is x over 1. Well, that's just the same as the hypotenuse divided by the adjacent side, and hence we get this picture right here. Now, let's go ahead and find that opposite side. By Pythagorean Theorem, we get h squared plus 1 squared is x squared, and thus h squared is x squared minus 1. And then if I solve for h, I get h is the square root of x squared minus 1. Of course, again, assuming in this triangle that the height of the triangle, that opposite side, is a positive value. So now we have all three sides, and we need that because we need to find both the cosine of this theta, but more importantly, we also need to find the tangent of this theta. And therefore, cosine of that angle theta is 1 over x. So just go up here, cosine adjacent over hypotenuse, 1 over x. And then we also need the tangent of that angle, opposite over adjacent. So that would be h over 1, but h is square root of x squared minus 1. And hence we get square root of x squared minus 1 divided by 1, which is just square root of x squared minus 1. So we found the cosine of that angle. We found the tangent of that angle theta. But of course, theta here just represents our secant inverse function. And remember, we previously established this first result here, that the derivative of the secant inverse function with respect to x is the cosine of the secant inverse function divided by the tangent of the secant inverse function. And just taking note that that secant inverse of x, again, is that angle theta. And we just found out that cosine of that angle theta is 1 over x. And tangent of that angle theta is square root of x squared minus 1. And hence we get that the derivative of the secant inverse of x is 1 divided by x times the square root of x squared minus 1. Now, we got to be a little careful here because depending on what's going on, we can have some different sign changes. And so let's just discuss this real quick because we're going to slightly modify that formula above to make it perfectly exact. And that is, take note that if this angle theta, secant inverse of x, is not negative, bigger than or equal to 0, but less than pi over 2, then that angle, of course, would be like in quadrant 1 in our plane, and our tangent of that angle, which we already established to be square root of x squared minus 1, would have to be positive because, both coordinates are positive there. And also, if the secant inverse of x, which again is our theta, is larger than pi over 2 but less than or equal to pi, then we're over there in that quadrant 2 arena, And our tangent of that angle theta is going to be square root of x squared minus 1, which we've already established, but it would be negative, right? Assuming, of course, we're not at pi, because if we're at pi, it would be 0. And above, if we're at 0, then we'd also be 0. So this is supposed to help us define the result that we got for the derivative of the secant inverse function more precisely. And that is, depending on what's going on with our secant inverse of x, that square root that we see in the denominator in our result can change signs. And thus, we finalize our result by this piecewise defined way of defining the secant inverse derivative, and that is it's going to be 1 over x times square root of x squared minus 1 if our x is bigger than 1, right? That's where that tangent will be positive. And then also it would be right here a negative 1 over x times the square root of x squared minus 1 if x is less than negative 1, and that's because in that situation that tangent of the angle would be negative, and hence we have to compensate for that. So this is our result, this piecewise defined function that gives us the derivative of the secant inverse of x. And maybe we suspected it might be piecewise based on that graph we saw earlier. Now, assuming that we do the same thing for the arc cosecant and the arc cotangent, we will come up with some results as follows, and that is the derivative of the arc cosecant, or the cosecant inverse function of x with respect to x, is this right down here. So it looks a lot like the secant inverse derivative, except the negative sign is flipped to where it occurs, right? So when x is bigger than 1, we get negative 1 divided by x times the square root of x squared minus 1. And if x is less than negative 1, then we'd have 1 divided by x times the square root of x squared minus 1. And again, this can be verified by going through a similar proof. Moreover, the derivative of the cotangent inverse of x with respect to x is a negative 1 divided by 1 plus x squared. And that's for all real numbers x, because remember the cotangent inverse function, the arc cotangent, looks very similar to the arctangent function, and it's defined for all real numbers, and it's smooth. And that wraps up the rest of the derivatives of the inverse trigonometric functions. Of course, this was a little more involved here than the previous video, but let's go ahead and just wrap up this video by looking at an example. So here's an example. Let's determine the equation of the tangent line to the function f of x, which is equal to secant inverse of e to the x at the point natural log of 2, comma, pi over 3. Now, note, e to the natural log of 2 is just 2, and of course that's bigger than 1. Now, why am I saying that is because our derivative of our secant inverse function that we came up with earlier was defined as different rules depending on the value of x, right? It was piecewise defined. And so because the input of the secant inverse here is e to the x, and once I plug in the natural log of 2 for x and I get 2, that's bigger than 1, and so we're going to use that first rule. So remember, just right here above, derivative with respect to x of the secant inverse of x is equal to 1 over x times the square root of x squared minus 1 if the value of x was bigger than 1. And so we're going to use that rule in figuring out our answer here to this question. And so let's go ahead and apply that rule. It follows that the derivative with respect to x of this function, secant inverse of e to the x, it's chain rule, right? So we're going to have the derivative with respect to x of e to the x, the derivative of that inner function, times the derivative of the outer function, which was right up there, right? Except now x is e to the x. So we get a 1 over e to the x times the square root of x squared, e to the x quantity squared minus 1. And then when I differentiate e to the x, of course, I get e to the x all over e to the x times the square root of e to the x squared is just the same as e to the 2x minus 1. E to the x's cancel. I get 1 divided by square root e to the 2x minus 1. So there's my derivative function here for this particular function, but we need to find the slope at this particular point. And so therefore, I'll find the slope by saying, well, the derivative with respect to x of the secant inverse of e to the x at now the location x is equal to ln 2. That's going to give me my slope of my tangent line. And so what's this going to be? We'll just plug it into the formula we just came up with. 1 divided by square root, or I'll plug in my ln 2. So e to the 2 times ln of 2, and then minus 1 inside that root. Now, remember, just off on the side here, e to the 2 times ln 2 power, that's just the same as e to the ln of 2 all squared. So e to the ln of 2 is just 2. Square that, you get 4. So in this case, I get 1 over square root of 4 minus 1, which is 1 over root 3, or if you prefer, root 3 over 3. Don't matter to me. So what do we got? We got a slope. We also have the point, ln of 2 comma pi over 3, and hence the equation of the tangent line. Let's write it down. Tangent line at the point ln of 2 comma pi over 3 is point slope formula y minus pi over 3. That's going to be equal to my slope. Let's just use root 3 over 3 times x minus the natural log of 2. And if you really prefer, we can bring that pi over 3 over and get y is equal to pi over 3 plus root 3 over 3 times x minus the natural log of 2. Bam, did it. And there you go. There's an example of using the arc secant derivative. And that's it for this video. So this video wraps up the derivatives of the inverse trigonometric functions. In the next video, we will generalize and say, what is the derivative of any inverse function, given that a function, of course, is 1-to-1. So until that next video, it's Matt and Beats. I'm out of here.